When an industrial electrical system fails, the result is instantaneous and violent. The equipment tears itself apart, releasing a concussive blast of superheated plasma that can vaporize metal in a fraction of a second. To understand this, look at the power grid for what it is: a massive reservoir of potential energy, constantly pushing against its restraints. Those restraints take the form of impedance. Every cable, transformer, and load on the network naturally resists the flow of electricity. It acts as an invisible, engineered barrier that harnesses that massive energy and limits how much current can flow at any given time. As long as the electricity is forced down that intended high-impedance path, our infrastructure remains safe. But the entire system balances precariously on that single condition. That balance can be undone by something completely mundane: a dropped wrench across two bus bars, a falling tree hitting overhead lines, or old cable insulation wearing thin. When one of these triggers creates an accidental connection, it forms a new, nearly zero-resistance path for the electricity to travel. The current completely bypasses the system's intended impedance. This is the literal definition of a short circuit. We can see why this is so dangerous looking at Ohm's law. Current, represented by I, is equal to voltage divided by impedance, or Z. When the impedance suddenly shrinks to zero, the current instantly skyrockets to its absolute maximum limit. In the space of a heartbeat, a microscopic mechanical failure turns a controlled stream of electrons into an unstoppable flood of energy. Compressing our timeline down to the first 20 milliseconds, we enter the subtransient phase. Depending on when the fault strikes, the alternating current wave experiences a DC offset. The wave is forced entirely in one direction, creating a single, massive, asymmetrical peak. That sudden surge of electrons generates immense, instantaneous magnetic fields wrapping tightly around the copper and aluminum wiring. These magnetic fields manifest as extreme physical pressure. Solid copper bus bars violently bow outward, threatening to rip the equipment off its mountings. Before the equipment even has a chance to heat up, the sheer concussive mechanical force of the short circuit begins tearing the system apart. Pushing the timeline forward, we enter the 20 to 100 millisecond window. The massive generators feeding the grid begin to physically react to the sudden lack of resistance, causing the fault current to decay slightly as we enter the transient phase. But that decay is relative. The current is still surging at unimaginably high levels, and the primary danger now pivots from mechanical stress directly into severe thermal overload. According to the principles of Joule heating, the thermal energy generated is proportional to the square of the fault current. The copper wiring carrying this load essentially becomes an industrial-scaled toaster coil. The internal temperature of the system's conductors skyrockets. Within a fraction of a second, the heat surpasses the melting points of both aluminum and copper. At the exact location of the fault, the voltage pushes through the degrading air gap, forming a 300-volt plasma arc. This arc instantly vaporizes the surrounding solid metal and rapidly superheats the air. When copper vaporizes, it expands to over 60,000 times its original volume. That sudden expansion of metal and superheated air creates the lethal concussive blast of an arc flash explosion. Surviving these physical forces requires managing them across a grid that spans thousands of miles. Operators monitor the network continuously, but human reflexes are far too slow to manually stop an event that unfolds in milliseconds. That responsibility falls to the circuit breaker. It operates as the ultimate line of defense, a heavy, mechanical device specifically engineered to endure the initial shockwave of the fault and extinguish the plasma arc. When the protective relays detect the massive current spike, they signal the breaker to trip. Heavy internal springs forcefully pull the physical contacts apart, stretching the electrical arc inside a chamber of vacuum or inert gas until the plasma chokes out. It is a purely brute force physical solution, and its success depends entirely on one single factor. The mechanical strength of the breaker housing must exceed the explosive energy of the fault itself. To guarantee that strength, engineers calculate the fault level, measured in kiloamps. This requires analyzing the entire grid architecture to predict the absolute maximum explosive energy available at every single node in the power system. If those calculations are wrong, the consequences are disastrous. An underrated breaker attempting to stop a massive fault will fail to contain the arc, melt internally, and explode like a bomb. This is why short-circuit calculations are a mandatory part of electrical engineering. It is rigorous, complex mathematical forecasting used to ensure that every single piece of protective hardware matches or exceeds the maximum potential threat it could ever face. The reliable electricity powering our homes and cities requires massive generation capacity, but keeping that system from tearing itself apart relies on continuous, precise mathematics and split-second mechanical engineering standing between order and explosive chaos.